Okay, welcome to Chapter 5 test review on essentially electrons. That's essentially what the chapter is about, the organization of electrons around the nucleus. Where Chapter 4 was the nucleus, Chapter 5 is about the electrons orbiting the nucleus. Chapter 4 and 5 is essentially atomic theory. And I kind of do it in one giant unit, but I test it separately. And we'll start off with what's an atomic orbital? An atomic orbital is essentially where you're finding electrons. What's the, where can you find two pairs of electrons? It's a point in space. It's kind of a vague, it's actually a little bit of a vague explanation, but it is, it's essentially, it's where you can find an electron. So, for instance, if I asked you to define atomic orbital, you'd say it's a region of high probability of finding an electron. We need to know the Aufbau principle. What is ground state? What is Pauli's exclusion principle? Heisenberg's uncertainty principle states that the impossibility of knowing both the velocity and the position of a moving particle at the same time. Because when you go to try to find it, then you're going to change its velocity. So you really can't do both at the same time. I have a test in front of me. Obviously, you're going to have to know what is an atomic orbital, Aufbau principle, Pauli's exclusion principle, Heisenberg's uncertainty principle. What's the Bohr model of the atom? What does it mean? What does it mean an electron moves closer to the nucleus or farther away from the nucleus relative to the stability and energy of the electron? What is the principal quantum number? We know that it's n, but what is it? We know that it's energy level. What's the shape of the p atomic orbitals? Well, they're dumbbells, where the S is a sphere. D is just very funky looking. It's kind of like four lobes, where the P has two lobes. Remember, how many electrons can you fit in each orbital? You can fit two. Opposite spins. Let's see. How many electrons can you fit in each of the sub-energy levels? Like S, you can fit 2, P 6, D 10, F 14. How many can you fit in? How many orbitals are there in each D? Well, there's 5 in D, 7 in F, 3 in P, 1 in S. What about what is the maximum number of electrons you can fit in each energy level? Remember, it's 2n squared. So 2 for 1, 8 for 2, 18 for 3, and 32 for 4. What happens when I irradiate an atom with energy and the electron jumps to a higher energy level and then comes back down to where it was and emits a photon or a quantum of energy? Quanta is plural, quantum is singular, and that's an emission. That's electromagnetic radiation. That's where electromagnetic radiation comes from. It comes from this kind of emission from the atom, from electron transitions. Let me read a question. What is the next atomic orbital in the series 1s, 2s, 2p, 3s, 3p? Boy, I hope you can answer that one. That's pretty easy. You're going to find, I think, some of you are going to find this very easy if you've been studying. Let me give you another question. Stable electron configurations are likely to contain blah. What's the answer? Stable electron configurations are likely to contain what? Remember, half filled and completely filled trumps other kind of partially filled. They're, a half filled energy level or a sub energy level or a full energy level are very stable. Noble gas configurations are very stable. Remember the exceptions. Remember the exceptions to the rule and why you have those exceptions. Why does 4s2 and 3d4 convert to 4s1, 3d5? Remember that half-filled 3d is very, very energy efficient, very, very low energy. So the Aufbau principle says that that's going to come first. That it's going to be instead of let's do the short form configuration of the 4s2 3d4. Well, it would be the nearest noble gas in brackets. Then it would be 3d5 4s1 if you're going to look at it, as it actually happens, because the electron will go into the 3d4 and become 3d5, so that you have a half-filled 3d and then a half-filled 3s, and that's more stable. That half-filled 3d is just incredibly attractive, so that's why that changes. You're going to find that as a question. What does it mean? And we didn't really go over it a lot, but we did go over it, and I made a nice video. You might want to look at the just a section, the chapter 5 lecture on light and spectroscopy. Remember, radio waves are long wavelengths. Gamma rays are short wavelengths. Red, orange, yellow, green, blue, indigo, violet. Red are long wavelengths. Violet are short wavelengths. So if I ask you which color of visible light has the shortest wavelength, it would be violet, Roy G. Biv. The speed of light is 3 times 10 to the 8th meters per second, or 3 times 10 to the 10th centimeters per second, and all light travels at that speed. All electromagnetic radiation is light. Remember, it's frequency times wavelength equals the speed of light. So if that's true, then the longer the wavelength, the larger the wavelength, the smaller the frequency. And the larger the frequency, the smaller the wavelength. Remember, energy also is in there. So think of it this way. Think of rope. All right, you have rope, right? And you have one wavelength of rope. That's it, right? One wavelength, and it's a very long wavelength, right? Very long wavelength. All right, now put that piece of rope on a table. One long wavelength. Now get some rope and make many short wavelengths. Okay, many short wavelengths, and that equal that one long wavelength in terms of distance. Okay, what's going to have a larger frequency? Okay, well, the one with the short wavelength is going to. But what's going to have larger energy? Well, the one with the shorter wavelengths is going to have a greater energy because it has more rope. There's more rope there. Okay, so you have to say, let's say you have one wavelength that's 1 meter long, right? 1 meter. So you have that on a table. You have a piece of rope, and you have this wave, and it's 1 meter long. The wavelength, one wave. Okay. Now you're taking another piece of rope and you're creating a wavelength of 1 centimeter. Okay, wavelength of 1 centimeter. But you're going to have 100. You're going to have 100 waves, 1 centimeter within, that are the same distance that the one wavelength is. So what's going to have more rope? Well, the one with the shorter wavelength is going to have a lot more. So it's going to be very high energy. So the gamma rays have much more energy than the radio waves. Remember, they're going both at the same speed. What is emission spectroscopy and what is absorption spectroscopy? So if you're going to look at a spectrograph, the emission spectroscopy is what's given off. That's what's given off by the atom. The emission spectroscopy is the energy given off. Well, the absorption spectroscopy is what's not given off. Okay, so it's what's missing. You have to know your scientists: Einstein, Schrodinger, Bohr, Rutherford, Planck, Louis de Broglie, Erwin Schrödinger. I did a video, look up scientists. That might be good to look over. A video named Scientists on my site. That might be good. 40 questions, 40 multiple choice questions. Shall I read a couple more here? What is the electron configuration of potassium? That's easy. Emission of light from an atom occurs when an electron, blah. Who predicted that all matter can behave as waves as well as particles? The wave-particle duality of nature. Ha ha. So that about does it. That's actually a pretty good review. It's a pretty good review. Let's see. I'm just looking at over things to see if I've covered everything. Let's see. As changes in energy levels of electrons increase, the frequencies of atomic line spectra they emit, blah. That's kind of weird. That's a weird one, but that's okay. That's a good one. So good. Okay. It says, here's one, you need to know specific wavelengths. This one's a little weird. This says, which type of electromagnetic radiation includes the wavelength blank? Well, I'm not going to give you the wavelength. It's a really small wavelength. All right, 10 to the negative 7th meters. That's really small. But which one is that? Is it gamma rays, microwaves, radio waves, visible light? So you have to be pretty familiar with that. I'm surprised I put that in there, but fair enough. Okay, well, that's your review. Good luck. Make sure you get a good sleep the night before the test. That's probably the most important thing. I know it sounds like you've heard that a million times, but I know for myself, even if I don't have a good sleep, I'm a mess the next day. So have a good day. Wish you well, and goodbye.